So this would probably come from, no doubt, just take aniline, treat it with HONO, sodium nitrite, HCl. This would give you your Diazonium. Some people just draw it N2+. Make sure you know the different ways to show it. Either way is the same thing. And then we would have I'll just cut that off, whatever the rest of that molecule is. Combine these two, and then you can get this to attack here and make that bond right there in the mechanism that we showed previously. Another example is Prontosil, the first real antibacterial that was discovered. Actually, an Azo Dye. Some biologist was using this to dye stuff. It had dye properties, but he realized that it killed bacteria. And he said, oh, look at this observation I just made. I can cure disease. And it was actually used, and in this handout there's a discussion of it. It's actually used as an antibacterial originally. But then later on they found out that this compound is not the active compound. In the body, this gets reduced and cleaved, basically cleaved, to just that and that. And somebody tell me what this is here on this side. Sulfanilamide, which you used in lab a couple of weeks ago. So about 20 years later, they realized that it was the cleavage product. It was actually the antibacterial. And so guess what? They just started giving this instead of the dye. Easier to make. Again, there's a handout that discusses some of that and how I think it, one of these compounds helped save the life of like FDR's grandchild or something way back when. So, Azo dyes have lots of applications. Next time you're eating something that has ingredients on it, look at it. Also your shampoos, anything that's colored these days can have FD and C number, whatever. Okay. Questions about diazochemistry? Substitution or coupling reaction? This week in lab, I think it's suggested in the timeline that you should consider doing the Diazonium reaction with your amine that was made last week. And the reaction is to replace the amino with an iodine. Okay? Let's try multi-step synthesis. Let's try this one right here. Actually, let me go back. Let's don't do it here. Let me just tell you some. Do we know how to put a chlorine on an aromatic ring? Yes. Chlorine, Lewis acid. Okay. Do we know how to put a cyano on an aromatic ring? We do now. Diazonium, copper cyanide. We don't know any other way. We didn't show any direct way. Question? Substitution of what? By what mechanism? Yes,
that was the only way we had learned it. It was in the lecture.
No, we haven't done any nucleophilic substitutions. Show me what you're talking about. We've not done any nucleophilic substitutions yet. We've only done electrophilic substitutions. The ring reacts with electrophiles. Maybe you've been looking at the golden sheet? You've been looking ahead?
Sure I haven't.
Okay. All right. Let's see why yours is apparently wrong. Okay, how do you put a cyano group on? You now have a reaction that's new to your toolbox. Diazonium. Okay? How many? Okay. Let's move to, I think, maybe the final handout before test time. But there's a lot here. We're now going to change gears. We're going to go back to ring chemistry. Hopefully this is showing up okay. Thus far, as I just mentioned, we've only reacted with electrophiles. Now we're going to react with nucleophiles. In general, we're going to do substitution of leaving groups on aromatic rings. We've not done that yet. There's a little warm-up. For example, if you have this compound here, we can react with this nucleophile. Hopefully you can distinguish between electrophiles and nucleophiles pretty much at this point. And the nucleophile replaces the chlorine. So we can label this as what? A leaving group. Everybody willing to consider that as a leaving group? It's leaving. Chlorine's a leaving group. So, what's the main mechanism we looked at before? Electrophilic aromatic substitution. The ring reacts with an electrophile. This is not an EAS because it's not reacting with electrophile, it's reacting with nucleophile. This is a nucleophilic aromatic substitution. NAS. We'll also see another mechanism called benzyne. Interestingly though, if you try to do the same reaction except instead of methoxy or nitro, it doesn't react. That implies that the nitro is very important. Okay? Now, this compound, same compound, if you heat it at 300 degrees, it will react, but it actually gives two isomers. The ethoxy replaces the leaving group, but somehow it gets on that carbon over there also. This is a different mechanism than this up here. This one requires a lot of heat. There's some warm-up questions there. Let's get into this. Hopefully there's another handout somewhere. Is there a white one somewhere? Can I not give us another handout? No, I'm sorry, it's in here. It's just not organized correctly for some reason. Okay, the back of the second page. The substitution of leaving group by nucleophile. Okay, some of this is a restatement of what we've already said. We're going to have a leaving group that we're substituting. And in EAS, what is being replaced on the ring? A hydrogen. Okay? The hydrogen did leave, but we don't typically call hydrogen a leaving group. Okay? Here we're going to have more classical leaving groups, halogens, other things, and really non-hydrogen. Leaving groups from the SN2, SN1, but this is not going to be those mechanisms. Okay? like a bromine. We're going to have a nucleophile. Since that's a nucleophile, the ring is an electrophile. Okay, we replace it, leaving group, very general. As I've already said, the mechanism is not any of these two. Reasons why. It's not EAS, because it's not an electrophile. The mechanism is either NAS or Benzyne. Let's first look at NAS. Let's show a mechanism for this reaction. Propose a mechanism. How can we replace this with methoxy? First off, this is Na plus and O minus, right? It's ionic. So we have OMe minus. Somebody propose the first step. What would you like to do? Well, let me give you some possibilities. Would you like the chlorine to just ionize off? And make that? And then have that attack? I mean, that would give that, but that would be an SN1. I mean, cation attack, that's SN1, right? It's not SN1. Do you want this to attack here and kick that off at the same time? That would give that product. Well, that's SN2. And it's not SN2. Right?
Can that chlorine do something?
What do you want it to do?
Maybe it's active.
Well, you got to be careful. You want these electrons to attack a minus? No. What type of reactivity do we have? This is a nucleophile. It wants to attack what? A positive. Do we have any positive here anywhere? I got a dipole here. Do you agree that there's some partial plus right there? Those are the dipole. You learn dipoles in Gen Chem. We learn them in Organic 1. It creates partial plus due to electronegativity difference. What do we have to do? We have to get this oxygen bonded to that carbon. The only reason I see it would like to bond there is there's some partial plus. And so these electrons are going to add here. Now when they come in, something has to go because carbon can only make 4 bonds. Which bond do you want to break? The sigma bond of chlorine? I'm going to draw that in very precisely. Which bond do you want to break? Sigma bond of chlorine or pi bond of carbon? Let me ask you more generally. Which bond do you want to break? The stronger sigma bond of chlorine or the weaker pi bond of carbon? Weaker pi bond of carbon. Didn't we do this about 4 weeks ago? Yes, this comes in and these electrons move here. What does that give? Methoxy now bonded there. Nothing happened here. What's now on this carbon down here? A lone pair. Electrons move here as a lone pair. Does this look like SN2? No. Does it look like SN1? No. It's neither of those. What did we just do generically? We did an addition. Yep. Okay. Is there any reason that we can invoke some stability here and say, hey, this has stability? Resonance stabilized. Electrons here. Electrons here. Question. The intermediate in our EAS, what was the charge of that intermediate? Positive, because the ring reacted with an electrophile. Here the intermediate is not positive, but negative, because it's reacting with a negative. We can do additional resonance structures. So, we do an addition to give a resonance stabilized anion. How do you want to get home? Let's just work from right here. How do you want to get home?
Reform gold bond, you can sell off.
That's a novel idea. How did you come up with that? Does it look familiar to what we did 4 weeks ago? Reform pi bond and kick off the better leaving group? What is that? What does this arrow movement give?
Ring reform.
It gives that. What do you want to call this? That was an addition. What do you want to call this? Elimination. Didn't we do addition elimination back when we did like tosylate or something? Yeah. It's not SN2. It's not SN1. It's an additional elimination that's more broadly known as what? Because what do we do overall? We substitute a leaving group with a nucleophile. Nucleophilic aromatic substitution. Okay. I just lied to you. This reaction as written does not work. This reaction does not work. It actually is that easy. This reaction doesn't work. Why does it not work? Well, the first answer should be apparently the energy of the intermediate is too high. It's too high a transition state. That's why reactions don't work. How can we lower the energy of this transition state? It's already resonance stabilized a little. How can we make it even more stable? How can we make this more stable? What if there was no resonance? How would you make this more stable? Give it resonance. Since there is resonance and you still need to make it more stable, how would you make it more stable? Give it more resonance. Or add electron-withdrawing groups. That would stabilize it if you have something to withdraw. This reaction needs electron-withdrawing groups either here, here, or here. Ortho to where it's happening, para to where it's happening, or ortho to where it's happening. We need, for example, a ketone. That would work. We add a ketone there. Add that in. We add a ketone there. And we're out of time. But now it will work. Why? Because now you have additional resonance structure. Please draw the additional resonance structure that we now have. The additional resonance structure makes it work. It's amazing how one more resonance structure will make it work. We're out of time. But, okay, go ahead, guys. Last questions. No. You just have to be stuck with it. Your reaction only works with a withdrawing group, ortho, or para. Please draw the additional resonance structure.
Is there any way you can know that the intermediate's too high? Or did it like
Just something we have to tell you. That's the observation. It doesn't work. That's the observation. But if you put the other group there, it will work. How do you know? This is based off of just what happened in the lab. Yeah, that has 10. It should only have 8. As itself, there's no reaction. Put this group there, and it occurs as drawn. Yes, it needs to be cool. That'll be stable.